Hey all, my name is Mukesh. In this video, we will talk about probability density function or PDF, which is a very important concept in probability. Also, we will see how PDF concept applies to a probabilistic model. In this video, we will talk about a step-to-step guide to translating a real-world scenario into a formal mathematical formulation. Let's start with a real-world scenario. In this case, it is a simple experiment which is drawing a single ball from a bag. So the scenario in brief, the object we are trying to mimic is a ball containing of 10 balls. Among those 10 balls, we have 5 different colors of 2 each. So as a step 1 of the mathematical formulation, we define the experiment. A random experiment is an action or process where the outcome is not known in advance. So for example, if we draw a ball from a bag blindly and with replacement, this is a random experiment. We don't know which color ball will be drawn out of the bag. In step 2, we define our sample space. So sample space is a set which includes all the possible outcomes of the experiment. Remember, our experiment in this case is an action of drawing a single ball from a bag containing 10 balls. So in this scenario, our sample space can be a red ball, blue ball, green ball, yellow ball, or an orange ball being drawn out. One point to note here is that we are drawing the ball with replacement. Coming to step 3, we define an event. So what is an event? An event is defined as a subset of the sample space. It can be like a simple event. So example would be the event that the single ball which is drawn out is red in colors. Or it could be a compound event, which is a collection of multiple outcomes. For example, drawing a ball that is either yellow or orange in color. Now we have to convert the scenario into numbers. So we define a random variable, in this case x. So x is a random variable which assigns a numerical value to each of the possible outcome in the sample space. In this case, we are denoting the outcome, which is the ball being red in color with a 1, it being blue as 2, green 3, yellow 4, orange 5. Now we come to the concept of probability distribution function. So probability distribution function describes how the probabilities are distributed over the various values of the random variable or the sample space. Since the bag contains 10 balls with 2 of each color, the probability of each outcome is the same. So in this case, the probability distribution function has a value of 2 by 10, since each ball is 2 for different colors, or the number of balls of different colors is 2. So here the probability distribution functions defines what is the likelihood of getting a variable with a value of 1, which corresponds to red, so on and so forth. If we represent it graphically, on the x-axis, we have the number denoting the each outcomes in the sample space, and the y-axis corresponds to the probability of that variable value occurring. So now, if we have to approximate the bag as a model, the probability density function would be a good approximation of it given our experiment. In the event of drawing a ball which is red in color, we can refer to the probability density function, and we can say that the probability of the outcome of the ball being red is 0.2. Similar is the case for the ball of other colors. So we have now approximated our first model. It corresponds to a bag containing of 10 balls, each with different colors, and each color being 2 in numbers. So here we define the experiment, the action, which is drawing a ball. We define a sample space, the possibilities. In this case, it would be the ball of different colors like red, blue, so on and so forth. Here we define an event, which is probability of drawing a ball and that ball being red in color. We define a random variable corresponding to all the possible outcomes in the sample space. And finally, we define the distribution or the probability distribution function. Now, in this case, the ball happened to contain equal number of balls of different colors, but that might not be a case, and it can happen that the color of the balls might be not same in number. So in this particular case, let's assume that the red balls were 4, blue balls were 3, green, yellow, orange were all a piece each. So the same concepts apply. It's just that the probability density function changes. And in this case, the probability of the drawn ball being red in color would be 4 by 10 because there are 4 balls in the bag containing 10 balls. Similarly, the probability for the balls of different colors being drawn out would be 0.3 for blue, 0.1 for green, yellow, and orange. Now there are 2 essential conditions which probability density function should adhere to or adhere to. Condition 1 is that the probability of each outcome occurring would be greater than 0. This makes sense because probabilities are generally a number between 0 and 1, both included. The second condition is that the probability of each outcome, the sum of the probability of each outcome should be equal to 1. So this is also true in our case. Now, if we plot the probability density function, it would appear something like this. So this is a non-uniform probability distribution function for an outcome which is discrete in nature. Now, though we have consider the outcomes to be discrete, it can happen that the outcomes are continuous. For example, if we pick up a kid in a class, and if the outcome is what is the height of that kid, the height value could be continuous. So in that scenario, the probability is an integration of x over fx. So that is the probability density function. So in this video, we have used the mathematical concepts in probability to kind of represent the bag by a predictive model given our random experiment and the event definition. Now, coming to AI models. AI models, they do not explicitly store the probability density functions, but they are trained in such a manner to approximate the probability density function. For example, LLM captures the probability density functions over tokens. So given a set of tokens, if we have to predict the next token, the LLM approximates it. So that was all in this video. I hope you found it useful. If you like the video, please subscribe to the channel as well as give a thumbs up to the video. Thank you.